Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I am your guide, Dr. David Irvin. We will continue with Chapter 1, Part 3. So what we're going to continue talking about is covalent bonding and how to track whether something has a polar covalent bond or a non-polar covalent bond based on the valence electrons and electronegativity. Okay, so if we want to do this, we want to do what we want to draw Lewis dot structures. Lewis dot structures help us take into account which electrons are going to be bonding to which atoms and where those and how many bonds they have in between. Okay, the first rule in drawing a Lewis dot structure is we need to determine the number of valence electrons on the molecular ion. Okay, what that means is we need to determine all the different electrons that are being contributed by all the different atoms. But again, we only want to use those valence electrons. For example, in carbon, that's our number 2 shell, okay? We then need to take into account the connectivity, basically which atoms are attached to which atoms. Once we figure that out, we want to connect each of the atoms with a single line between those atoms. What that represents is a covalent bond, and that single line represents 2 electrons, okay? So we need to keep track of that. Then we need to arrange the remaining electrons around each of the atoms so that it has a complete valence shell. For most of the atoms we're dealing with, like carbon, oxygen, nitrogen, and the halides, we're looking for a total of 8 electrons around each of those atoms to fill that valence shell. Occasionally we'll have more or less. For example, hydrogen only has 2, and things like sulfur and higher can have more. But for the most part, we're looking for 8 electrons around the atoms. Then we're going to show which bonding electrons are there, and we're going to show those as single lines, making sure that those are 2 electrons. And we're going to show all of our non-bonding electrons as lone pairs or 2 dots, okay? Those non-bonding ones are the ones that aren't shared but are required to have the full number of valence electrons, okay? So then if an atom shares 1 pair of electrons, that means it has a single bond. If the atoms share 2 sets, 2 pairs of electrons, that means it has a double bond. And it can even share 3 sets and have a triple bond. So by looking at the number of lines we have, we can start counting electrons and filling in all of the gaps, okay? So as we looked at before, we can look at the number of valence electrons by stop sharing and re-sharing our screen here. Right here, we can go to the table and say, okay, yeah, we have, for anything in our group 1A, we have 1 valence electron, and then 3, 4, 5 tells us how many valence electrons we have. Remember, we don't have to memorize this table, we just have to have access to our table of elements right here. The group numbers that we have right here at the top tell us how many valence electrons we have. 3 valence electrons, 5 valence electrons, 7 valence electrons. So all of our halogens have 7 valence electrons. Carbon and silicon have 4 valence electrons. So that's how we use the table. Again, you don't have to memorize it, just look at your periodic table of elements. Okay. So how can we do that to help us draw something? Well, let's start with something in general, something simple that we can play with that we might know about. Let's say we have 2 hydrogen atoms and 1 oxygen atom, and we need to draw a Lewis dot structure, not knowing anything more than we have those 3 atoms, okay? So the first thing we have to think about is, okay, hydrogen has 1 electron on it. Oxygen has 6 electrons on it if we look at where it is on the table. So if oxygen has 6 electrons, and we have a total of 2 hydrogens with 2 electrons each, that means if we put 2 hydrogens on the outside of an oxygen, we should have 8 electrons. All right, let's see if that's true. So we're going to start with having our 6 electrons for our oxygen here. Now I'm going to change colors here. I'm going to turn the hydrogens into blue so we can follow those electrons right here. So if we have an electron by this hydrogen donated here and an electron from this hydrogen donated here, we now have a total of 8 electrons around oxygen, and hydrogen only needs 2 electrons around it. And so there's 2 electrons that are shared with hydrogen. So we've accounted for all of our valence electrons, and now we need to account for where the bonds are. So what we're going to do is we're going to say this hydrogen here, these 2 electrons here formed a single bond between hydrogen and oxygen. So we're going to draw that there. And then the oxygen's there, and then these 2 electrons form the next single bond between hydrogen and oxygen. But we're not done yet, because there are still 2 lone pairs we have to account for, these and these. So we're going to put those back on the structure here. And so we end up having a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen, and we have 1, 2 electron around each of the hydrogens. Okay, remember, bonds count for 2 electrons, and they're shared between those 2 atoms, so they count for each of the atoms. Okay, let's do it again with something like, let's take 4 hydrogens and 1 carbon, okay? So if we look at where carbon is on the periodic table, we'll see it's in an A4 group, which means it has 4 electrons on the outside of it to start with. And we know that hydrogen has 1 electron on each of those there. So let's start with drawing our configuration. We have 4 hydrogens, we have a carbon, and we think it can bond 4 times. So let's draw our lines like this and showing our connectivity. Right here. Okay, let's see if everything has the right number of electrons. Okay, hydrogen, since this bond is 2 electrons, right, we can say that this hydrogen has a total of 2 electrons. That's all it can have, so it's happy. And each of the other hydrogens now also have 2 electrons. So, but if we look at carbon here, we have 1, 2, 3, 4, 5, 6, 7, 8. Carbon is able to share those 8 electrons, and therefore it has a complete outer shell. So, what's important to note here is that we have 4 bonds to carbon, and it's bonded to hydrogen 4 times, 4 different hydrogens, but there are no lone pairs because all 4 of its valence electrons are being shared with the 4 bonds to hydrogen. Okay. Let's do one more. Let's do something a little different. Let's do, we have 3 hydrogens and we have 1 nitrogen, okay? So if we look at that, hydrogen's still group 1. Nitrogen is group 5A. So let's think about that. That means there are 5 valence electrons on nitrogen. So if we start with a nitrogen and we're going to draw a bond to hydrogen, and we're going to draw a bond to our second hydrogen, we're going to draw a bond to our third hydrogen, okay? But nitrogen had 5 electrons. So we had 1 electron shared here, 1 electron shared here, 1 electron shared here, which means we have to have 2 more electrons on nitrogen. So that gives us a total of 5 electrons that it brought to it. Now hydrogens each brought 1 electron. So now we've accounted for all the electrons we brought to the party. And so now we have 3 bonds to 3 individual hydrogens, and we have a single lone pair here, okay? So keeping track of this lone pair is going to help us with whether or not the compound is polar or whether or not the compound, what shape it might have. So we want to keep track of those, okay? There's a couple more here in the corner. Go ahead and try to figure those out on your own using these rules to see if we can do it. Now, the next thing we're going to do is let's try a couple more, a little bit harder, okay? It might kind of give us a little bit of a strain. So one common material we have would have something like 2 hydrogens, 1 carbon, and 1 oxygen, okay? That's getting a little more complicated here. So the hydrogens have 2 electrons because there's 1 electron for each of those hydrogens. The carbon we know has 4 electrons. And the oxygen, because it's in group 6A, is 6 electrons. So we have a total of 12 electrons we need to play with, okay? So let's start arranging things around here and see how we have. And a lot of the times, we want to try to put carbon in the middle. It just seems to help a lot of the time. So we have a carbon here, and we want to bond it to an oxygen, we want to bond it to a hydrogen, and we want to bond it to another hydrogen here, okay? So When we do that, all we've done is created our structure right here, and we have 1, 2, 3, 4, 5, 6 electrons, 2 electrons for each of those bonds, right? So we have 6 electrons, but we have 12 electrons to play with here. So now we got to distribute those other electrons here. Okay. Now, if I remember correctly, carbon had 4 electrons around it, right? So we have 1 electron shared with this hydrogen. Let's change colors here. We had 1 electron that's shared to that hydrogen, 1 electron that's shared to that hydrogen, and 1 electron shared to this oxygen. That means we have another electron somewhere. So we're going to have to put another electron around oxygen. I mean, a carbon here. Oxygen here, I'm going to draw it in green now, had 6 electrons. So this is one of the electrons. And so we have 1, 2, 3, 4, 5, 6 to put around there. Oops, 1, 2, 3, 4, 5, 6. Oh, there's an extra electron there. Counted too many. So now we have 6 of these green electrons right here. Now we know that electrons that are lone pairs, that's okay. But we have an unpaired electron on carbon here. We have an unpaired electron on this oxygen here. What if we just put those together and made a second bond with those 2 electrons? Now let's see what that gives us here. Okay. What does that give us? It gives us 1 bond here. So the hydrogen has 2 electrons. It's happy because 1 electron from the carbon, 1 electron from that. We have hydrogen here. We have 1 electron from this hydrogen, 1 electron from the carbon. It's got 2 electrons. It's happy. We have 1, 2, 3, 4 electrons that carbon started with, and then it's sharing 1, 2, 3, 4 more, 2 with the hydrogen and 2 with the oxygen. So it has 8 electrons around it. And now we have 1, 2, 3, 4, 5, 6, those 6 electrons it started with, plus 2 more electrons, giving us the oxygen has 8 electrons around it. Okay, now let's look at the total number of electrons though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have the 12 valence electrons we started with, and because we didn't have enough shared electrons with 2 of the atoms, we made our first bond, and then we made a second bond to get those shared atoms. Okay, I'm going to do one last one, and then you have some other things down here at the bottom that you can try yourself. But the last one I want to try is I want to have 2 hydrogens and 2 carbons. Okay, so hydrogens, that's going to give us 2 electrons. The carbon is going to give us 8 electrons, meaning we want a total of 10 electrons at the end of the system. Okay, so if we have carbon, we're going to bond our structure. Let's just start with something like this. And we know carbon had 1, 2, 3, 4 electrons on it. 1, 2, 3, 4 electrons on it. Let's see, the hydrogens each brought 1 electron to the party right here. And we have, unpaired electrons here. So I think if we made these 2 electrons a bond and these 2 electrons a bond, that would make it have a right number of electrons. We have the right number of electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have the right number of bonds to the carbon, right? Because let's start counting these. So we have 1, 2, 3, 4, 5, 6, 7, 8 that are shared with this carbon. So that carbon has 8 electrons. Here we have 1, 2, 3, 4, 5, 6, 7, 8 shared with this carbon. This carbon has 8 electrons around it. This carbon has 8 electrons around it. This hydrogen has 2 electrons around it. This hydrogen has 2 electrons around it. So each of those elements has their own number of electrons, and we have a total number of 10 valence electrons. But that's a little messy. How would we end up redrawing this to be the way it should be? So we have a carbon with a single bond bonded to a hydrogen, but then we have 1 bond here and 1 bond here. So that means we have 3 bonds in between 1 carbon to the next carbon, giving us our net Lewis dot structure. Okay? So what that kind of does is show you where the electrons come from and kind of how to start the structure. But one of these, a couple little rules that'll help you kind of identify where things are is carbon usually has 4 bonds, okay? In fact, it'll have 4 bonds or a charge, and so it typically has 4 bonds with no lone pairs. So you want to bond 4 lines to carbon. Nitrogen tends to have 3 bonds plus 1 lone pair. So you want to bond 3 things to nitrogen and have a lone pair there. Oxygen tends to have 2 bonds and 2 lone pairs. Halogens like fluorine, chlorine, and bromine tend to have a single bond to something and then 3 lone pairs. And hydrogen only has the 1 bond and no lone pairs because it only needs 2 electrons in its outer shell. So if you follow these simple rules and go back and do those, suggested elements down here, you'll see that it makes it very easy to put the structure together and make sure you have the right number of valence electrons. Okay, so now let's say you've drawn your Lewis dot structure and that you've arranged it correctly, but there doesn't seem to be the right number of bonds here and there. That could happen, and that's because you can have where there are shared or unshared electrons that are or are not bonded to an atom. And when that happens, we can actually have a charge on the atom. What we call that is a formal charge, meaning if it has too many electrons on it, it'll have a negative formal charge. If it has too few electrons, it'll have a positive formal charge. So the way to think about that is you're going to take the number of electrons you have and try to figure out whether they're evenly shared or unshared. And so the way we can think about that is that our formal charge is equal to the number of valence electrons in the neutral unbound atom, okay? So for example, if we had 1 carbon and 4 hydrogens, that is a total of 8 electrons. So you're looking at the total number of valence electrons in the neutral unbonded atom. And then you're going to subtract all unshared electrons, meaning lone pairs, because that lone pair is on the atom itself, it is not shared. And 1/2 of the shared electrons, anything that has a bond in it, you only get half of those electrons, because remember, you're sharing them with the other atom. You only get them half the time, therefore they're only 1/2 of the bonded. So you have the total number minus unshared or electron pairs plus 1/2 of the bonded electrons. Okay. And so what we're going to do is we're going to use that equation to help us calculate the charge on a couple different things. Okay. So let's go and apply this to our thing. So the first thing we're going to do is we're going to draw a Lewis dot structure using those rules from before. And then we're going to figure out the formal charge on things. And I'm going to do these 2 in red, and I want you to go back and do the other remaining ones, okay? So if we look at the 2 in red, let's start with this nitrogen with hydrogens on it. So we have a nitrogen right here. And we have 4 hydrogens bonded to it. So it's 1, 2, 3, 4. Hydrogen, 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 and a hydrogen here. And it says it has a positive charge here. So where is the positive charge? That's what we need to figure out, okay? So hydrogen had 1 electron right here. And we're going to subtract the number of unbonded lone pairs. We have, how many lone pairs do we have around hydrogen? We have 0 lone pairs. Remember, it only needs 2 electrons, so we have 0 lone pairs. And we want to subtract, it's plus 1/2 of the bonded electrons. We have 1, 2 electrons. We have 2 electrons that are bonded to that, 1 and 2. So we get 1/2 of 1 is equal to 1/2. 1/2 of 2, so that gives us a number of 1. So our formal charge is equal to 1 minus 1, which is equal to 0. So the formal charge on hydrogen is 0. Now, if we did that for all of the other hydrogens, we would see that those are all 0. Okay, that means the positive charge must be on the nitrogen. But let's prove that to ourselves here. Okay, nitrogen, when we came in to this, it currently has 8 electrons around it, but when the formal charge for nitrogen is equal to the number of valence electrons it started with. Okay, it's in group 5A. That means that it had 5 electrons to start with. Okay, so we need to subtract from that. We have no lone pairs now. We have 0 lone pair electrons plus 1/2 of the bonding electrons. We have 1, 2, 3, 4, 6, 7, 8 bonding electrons. So 1/2 of 8 is equal to 4, minus 5 is equal to the formal charge, and 5 minus 4 is equal to plus 1. That means that nitrogen has a +1 formal charge. Okay? So let's apply that again, okay? Let's apply that again, but let's do it to this NO2 plus, okay? We're gonna do the same Lewis dot structure, try to get the same correct number of bonds we had on it, and we're gonna see where we get that formal charge is gonna go, okay? Okay, dun, 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 dun. All right. So let's start with this one right here, and we have 2 oxygens, and they each brought 6 electrons, right? And we have 1 nitrogen, and it had 5 electrons to start with. Okay, so when we have 2 things and 1 thing, we want to try to put the 1 thing in the middle. So we're going to have nitrogen there. And oxygens want to bond twice, so let's just start with it there. And we say the whole thing has a plus charge, okay? So, there's lone pairs on the oxygen, right? Because those are the 2 lone pairs on the oxygen. And it tends to bond twice. So if we look at oxygen here, we have 1, 2, 3, 4, 5, 6 electrons, 7, 8 total, counting the bonds. All right, so let's look at the formal charge of just this oxygen here. Formal charge is equal to the number of electrons it brought with it, which was 6. That's because it's in group 6A. And we have subtracting 1, 2, 3, 4 electrons from the non-bonded electrons. Okay. And then plus 1/2 of the shared electrons. We have 1, 2, 3, 4 shared electrons. 4. Okay. 1, 2, 3, 4. 1, 2, 3, 4. So that means that 1/2 of 4 is 2 plus 4. Okay, which that is 6. So the stuff inside the bracket is equal to 6 minus 6 means the formal charge on oxygen is 0. Okay, let's do that same equation, but now let's do it with the nitrogen here. So that was with the oxygen. Let's do it for the nitrogen. Okay, so I'm going to change colors here so that we can keep track here. So if we want the formal charge on nitrogen here, is equal to the number of electrons it brought, which is 5, minus non-bonded electrons. We have 0 lone pairs right now because there's 1, 2, 3, 4, 5, 6, 7, 8 electrons around nitrogen, but they're all shared with oxygens. So we have 0 non-bonded plus 1/2 of 1, 2, 3, 4, 5, 6, 7, 8. So 1/2 of 8 electrons. So we have 1/2 of 8 electrons. So 1/2 of 8 electrons is 4 electrons minus 5 because it had 5 electrons to start with, meaning the formal charge on nitrogen is equal to plus 1. Okay, so I want you to go ahead and do that for the remaining ones here. Start with putting, if you have multiple things, you want to try to put see how many things you can attach to the center atom. Track all of your electrons in your Lewis dot structure, and then look at how many electrons are shared, how many electrons are lone pairs, and subtract from the number of valence electron it brought to the molecule. Okay? So let me do two more just to drive it home. Okay? So the one I'm going to do here, I'm just going to do one more, actually, right here, the nitrogen here. Okay, so we have 3 nitrogens, okay? Each nitrogen brings 5 electrons because it's group A. All right, so let's try to draw this nitrogen compound here. And we have nitrogen, nitrogen, so we have to draw it like that. Right here, let's see, we have a negative charge, so we have to think about that as well. Okay, so nitrogen has to have, let's say, right here, so 1, 2, 3, 4. 1, 2, 3, 4. Let's see. Nitrogen brought 5 electrons. Let's just start with putting the 5 electrons around each of the nitrogens first. Okay, so we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so each of the nitrogens now has 5 electrons around. 1, 2, 3, 4, 5. Okay, but this only has 6 electrons around it, so that means it needs to share an electron. So we're going to move this electron in and this electron in to give us a new double bond here. And so that takes that electron away and that electron away. Okay, so we have 1, 2, 3, 4, 5, 6, 7 electrons around this nitrogen. Ooh, that's not very good. So let's share this electron with this electron here and give us another double bond there. Okay, so that's interesting. We have 1, 2, 3, 4, 5, 6, 7, 8. So this nitrogen has 8 electrons around it. This has 1, 2, 3, 4, 5, 6 electrons around it. So we probably can't do that either. So let's try to share those electrons this way. Let's take those two, put them back here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7. Ooh, let's make a double bond here and take away these 2 electrons right here. And that gives us 1, 2, 3, 4, 5, 6, 7, 8 around this electron. And we have this electron sitting here by itself, okay? And we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. We have 1, 2, 3, 4, 5, 6, 7 electrons. But we have another electron. Remember, we have our negative charge. So we have to add 1 more electron to this because of the negative charge to give us a total of 5 times 3 plus 1 is a total of 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. All right, our Lewis dot structure is now correct. We took the 5 electrons from each of the nitrogens we had, plus the extra electron from the charge here to give us our Lewis dot structure here. Okay, so now that we have our Lewis dot structure done, we can calculate our formal charge, okay? So let's calculate formal charge for this nitrogen first. That's very narrow. Actually, yeah. Let's calculate our formal charge for this nitrogen here, okay? So formal charge, ooh, again, why is it narrow? Okay, formal charge is equal to the number of electrons it brought with it, 5, minus non-bonded pair, 1, 2, 3, 4, 4 nitrogen, 4 right there, plus 1/2 of the bonded electrons, 1, 2, 3, 4. So 1/2 of 4, okay? So that's 1/2 of 4 is equal to 2. And so we have 4 plus 2 So that makes it 6. So we have 5 minus 6. So our formal charge on this nitrogen is minus 1. So this is minus 1. Ooh, we have a minus 1 here already. Cool. Maybe that means we're balanced out. Okay. So that was the formal charge on this nitrogen is minus 1. All right, let's go back and calculate the next one. I'm going to do it in another color to make sure we don't mess up our electrons that we're counting. Okay, so let's do it in another color here. So if we do the formal charge on this nitrogen here, formal charge is equal to 5, because we had 5 electrons, okay, minus non-bonded, there are 0 lone pairs here, plus 1/2 of the bonded, 1, 2, 3, 4, 5, 6, 7, 8, 1/2 of 8 electrons gives us 4. So 4 minus 5 gives us a formal charge of plus 1. Ooh, the formal charge on this nitrogen is plus 1. Okay, plus 1 minus 1, so, okay, but the net result here is a minus 1. Okay, let's measure the last one. We can't just skip it. We gotta measure it or calculate it. So let's calculate this last one. And let's do it in green right here. So we're gonna do this last one right here, this nitrogen in green. And we start with, again, the formal charge is equal to the 5 electrons it brought with it, minus lone pairs, 1, 2, 3, 4. We have 4 non-bonded lone pair electrons, minus 1/2 of the shared, 3, 4. We had 4 shared electrons. So 1/2 of 4 is 2 minus 4. I'm sorry, we're adding that right there. So we have 5 minus 6, because the sum of this bracket here is 6, is equal to a formal charge of minus 1. So that means this nitrogen also has a minus 1. Okay. How can that be? Our formal charge of the center nitrogen here is plus 1. So a plus 1 and a minus 1 equals 0, but then we have another minus 1. So the net charge on the entire molecule is minus 1. Hey, wait a minute. It is minus 1. Our net charge is minus 1. So the molecule as a whole has a charge of minus 1. But one nitrogen has a -1 formal charge, one nitrogen has a +1 formal charge, and one nitrogen has a -1 formal charge. So one of the pluses and minuses cancel out to give your net molecule a formal charge of -1, and the individual atoms sum up as well. Okay, so that concludes this section of 1.3 of our bonding with Lewis dot structures.